Harry, thank you so much for joining us today. I'm very excited to hear more about biochar, learn more about it. If you don't mind just introducing yourself to our audience.
Okay, thanks, Maria. My name is Harry Grote. I'm an associate with Dovetail Partners, and I've been working on biochar related topics since about 2015 now. And I'd like to welcome you and thank everybody for checking this video out. It's largely based on a presentation made in August of 2023 for the U.S. Forest Service, and I've included some updated material with this redo as well. But first, let me introduce Dovetail Partners. Dovetail consists of a diverse group of individuals who are highly skilled in various aspects of the natural resources universe. Each of us are experienced in a variety of areas of utilization and management of natural resources. While we work to advance the knowledge base of land use and the use of natural resources, we rely on established science to do that. I hope you'll see that reliance on the science of climate and biochar in this presentation. Personally, I find it helpful to know where a speaker is coming from. So this is my perspective. As an engineer, I explain to folks unfamiliar with that profession that we use science to solve problems. From my career spent looking for optimal solutions and from solving problems, I've come up with two guiding principles which have served me well in life, business, and my tenure with Dovetail. The first is taken from an ad campaign by the Caterpillar Company in the 70s, which I felt was really on target. So I've proudly conscripted it and used it with clients ever since, while tackling complicated problems constrained by time, budgets, and the practical application of the relevant science. The second principle is one which I've repeated to myself and others many times over the years, to focus attention on getting the best holistic solutions in place possible. I see the production, use, and application of biochars as one of the most holistic solutions to a host of issues I've ever encountered, and I plan to explain why during this presentation. Two assumptions I'd like to state at the outset are that the global climate is reacting to the movement of carbon into the atmosphere. The data are pretty conclusive about that, and we're seeing increasingly atypical climatological effects from that buildup in real time. It's widely agreed, at least in the scientific community, that we need to reduce atmospheric carbon, and sequestering it in terrestrial settings seems to offer the best solution. The next slide is a favorite descriptive graphic of mine, which originally came out in the early stages of the pandemic and was updated shortly thereafter. It presents a perspective which illustrates the magnitude of the issues of the time, but doesn't really capture the fact that while we focus on local and national reactions to these issues, they're global in scope. I want to quickly define a few acronyms I'll be using. CDR, carbon dioxide reduction or carbon dioxide removal. The IPCC consists of hundreds of scientists who use the climate-related reports, or who issue the climate-related reports we've all seen. Probably the most memorable being the one in 2018, setting 2030 as the deadline for limiting global warming to 1.5 degrees C. IBI is the global advocate and clearinghouse for all things biochar. There are many national groups around the world. USBI is the one here in the States and offers an outstanding array of information and links, as does IBI and other national organizations. Now I'm going to tackle the subject matter for today. As our problem definition, to which biochars are a partial solution, is that climatological changes driven by increasing amounts of atmospheric carbon are producing unwanted consequences. Like the proverbial Gordian knot, it's a tangled web of interconnected issues defined by the single moniker of climate change. Just as it's a complex problem, though, the solution is also complex. So climate change mitigation is a wicked solution. All the facets of the problem have to be addressed simultaneously, or at least in logical order to be effective. In the case of biochars as a mean to sequester carbon, the science is sound, but the other aspects are evolving slowly. Okay, let's look at how biochar might be part of a solution by defining what it is. Biochar as a label or a word is a lot like the word soil. It describes a physical product with varying characteristics. It's pretty commonly accepted that biochars are a product of pyrolysis, which is heating organic feedstocks in a low oxygen environment. I'll illustrate that with a graph here in a minute, but higher processing temperatures generally produce chars with higher percentages of stable carbon. The name biochar originally was coined for the use of these chars in biological settings. But over the years, it's become a term used for all the high temperature chars, which can be used in a host of applications. Over 55 end uses have been identified and or piloted, though soil incorporation has historically been the most prevalent. I've made biochar from hardwood, softwoods, and grasses. But as you can see, any number of feedstocks can be used, each with a different set of characteristics, so that the char needs to be matched to the end use carefully. Biochars have been called out as a CDR product since the earliest IPC report there in 2018, which laid out the 1.5 degrees C global temperature rise target. And it's been called out repeatedly in most of the reports since then. Biochar is a commercial product which has been growing increasingly in importance as a CDR strategy, as well as being recognized for its many co-benefits based on both research and application experience. Biochar production has been growing, as estimated by the IBI, at about 30% a year recently, as more and more buyers recognize its potential. But as far as making a substantial contribution to global CDR, it's got a lot of ability to scale up. As IBI has been promoting it, the product is safe, the technology is scalable, and the industry is shovel ready. Given the fact biochar is the current leader in the carbon credit market, it's at least being recognized for its CDR potential from that sector. And hopefully that investment will allow the production of biochar to continue to grow quickly to its full potential as a CDR solution. Here's a graph I like to use to illustrate the various key aspects of biochars. While this is for one hardwood feedstock, the curves are generally similar in other feedstocks. Organic matter is about 50% of the carbon in the original feedstock, and that's what's left after pyrolyzing the feedstock, which you can see with the black line. The carbon matrix is what's left after the volatiles are cooked off. I explain this transition as the dividing line between charcoal for fuel and biochars for sequestering carbon. Note the yellow line, which is kind of hard to read, which represents surface area, and how it spikes in the green shaded optimum pyrolysis temperature range. Surface area is a very important characteristic for biochar since it defines the spaces within which can hold water and areas in which the carbon matrix can bind with or hold on to nutrients, contaminants, or other target chemicals depending on the application. For biological applications, those spaces also serve as homes for microorganisms in the soil or compost. The pH and cation exchange capacity lines track characteristics important for matching with appropriate applications, especially in soils, stormwater treatment, and remediation applications. I want to highlight the bulk of science behind biochars. This one reference is a great one, I think, for highlighting biochars' use in agricultural applications. It illustrates that the science of biochars has advanced sufficiently to where we have meta-studies of meta-studies. There were over 5,000 biochar peer-reviewed papers published in 2020, and that number has been steadily increasing for over a decade now. The next slide is a figure from a recent Dovetail report on CDR, specifically focused on natural CDR. While the natural climate change solutions in the blue highlight is impressive in its potential, we need an everything, everywhere, all at once approach for effective global CDR. So looking at the potential of biochar production, which is there in red, it encompasses both BECCS and which is bioenergy plus carbon capture and storage, and the pyrolytic carbon capture and storage solutions. You can see biochar's superpower is that it's currently an available technology and product, and when made from woody feedstocks, especially from wildfire reduction thinnings and cleaning up harvest slash, it has the co-benefits of reducing wildfire risk, which has become a significant contributor to atmospheric carbon buildup and particulate pollution. You can read the Dovetail report shown there at the bottom for a fuller understanding of CDR potentials and constraints. I'll discuss other co-benefits of biochar in a minute, but this example dovetails nicely with the wicked solution idea. And you can see here micro photographs of various feedstocks of the huge surface area within biochars. The next slide gives an even better perspective on the surface area. One of the most significant characteristics of biochars are the massive surface area they offer, and from which most of their co-benefits derive. What you see here is the carbon structure left behind after pyrolysis. You can compare these post-processing pictures with the original feedstock and find they look almost identical structurally. However, the biochar has much more open area than the original feedstocks, since everything but the carbon matrix has been cooked off. As an example, hardwood biochars I've made have a surface area of 188 meters square per gram. So 250 grams, or about half a pound, would have the surface area equivalent of a professional football field. This graphic was developed as part of a series of fact sheets to provide insight to the breadth of benefits biochars offer beside its carbon sequestration capability. This one and a series of fact sheets are accessible at both the Dovetail and USBI websites. Commercial production of biochar is in the tens of thousands of tons per year range in the US and the hundreds of thousands of tons per year globally. But as we saw in the earlier chart, it needs to grow considerably. There is also a substantial but unrecognized production of biochar voluntarily. Do it yourself by advocates and by families who cook and heat using primarily woody and residual agricultural feedstocks. These are considered to be lower technology generators, but may be a significant contributor to carbon sequestration, as most of the biochars they produce are used to enhance crop production, much of it for subsistence farmers who, through personal experience, have been convinced of the value of the char they produce. The UN Food and Agricultural Organization estimates that there are over 2 billion people globally who heat or cook with wood or ag residues like crop waste, stover, and dung. Imagine if each of them produced a kilogram of biochar a day, how much impact that might have on CDR globally, since each unit of carbon sequestered is equivalent to 2.8 units of CO2. There are a number of organizations working in less developed countries to educate about and expand the production of biochar as a co-product of heating and cooking. I'd add personally, they need financial support if for no other reason than credit for their contributions to CDR. As I noted earlier, biochar has been the leading carbon sequestration tool. However, carbon removal prices, which are for long-term storage, command significantly higher prices than for offsets of carbon emissions, which is a reason the market is slow to grow. As you can see, the carbon removal credits are between $100 and $500 a ton, but for offsets, they're in the single dollar range. To date, most biochars have been used in soil applications. The historic aspect of biochar research has been focused on those applications and have found these benefits in varying degrees. While biochars have seen most crop productivity benefits in what are considered poorer soils, their CDR potential can be realized as a standalone contribution. However, in the aforementioned less developed regions where biochar production is being adopted, they're almost universally working with poorer soils, so they really appreciate these co-benefits. As mostly subsistence farmers, the improvement in crop yields alone can be life-changing. Here are some specific agricultural applications for biochars which are in use currently. There are non-ag uses for biochars. All these applications are being or have been trialed successfully. Their use more widely, thus sequestering larger volumes of carbon-rich biochars, requires more investment, policy and regulation changes, and willingness by the industrial sectors to expand applications. All these can be considered to be permanent carbon storage in that they won't break down much, if at all. Recent research on biochars in soils have shown that at least 74% of the carbon remains stable for at least 100 years. A series of reports by Dovetail targeting specific ag applications showed a significant market potential for expanding carbon sequestration with biochars, as well as offering productivity benefits. Note the immense opportunity with manure management, which does not include its use in digesters. Another huge market is the addition of biochar in compost at between 10 and 25%, which has been proven to have significant co-benefits to the composting process, as well as to the crops it's ultimately used. Let's look now at what's holding biochar's adoption back. Like soils, biochar's characteristics vary. For soil applications, since biochars are a manufactured product, the feedstock used, processing time and temperature, the processing technology, and any pre or post processing treatments all affect the characteristics, which makes them different than homogeneous products like most soil amendments. Matching characteristics of the char and its application is critical and requires additional time for analysis and knowledge of making those connections. Carbon credits affect the final price and are in an evolutionary state, so are also variable and have their own associated costs. Using the heat of pyrolysis makes a huge difference in the cost of biochars and in the carbon balance of any given char or technology. And there's also the consideration of the generation of co-products like syngas, bio-oil, or pyroligneous acid, also known as wood vinegar. All these factors affect the cost of the char, whether made for profit or personal use. To summarize, the uses for biochar are many, but the markets are still developing. As you've seen, biochar has many co-benefits as a product and as a climate change mitigant. It's safe, scalable, and shovel-ready as a technology and a product in a wide array of production technologies. And again, the carbon credit opportunities will hopefully spur investment in expanding biochar's production. And the last item is that the 2030 target for the 1.5 degrees C global temperature rise is only 6 years away. I want to touch again on the low-tech biochar potential. With close to 3 billion users of firewood for heating or cooking, there's a lot of opportunity for biochar production in that sector. The low-tech producers are typically self-funded or philanthropically funded. They're also growing at a significant clip and are largely unrecognized contributors to CDR in the current scheme of things. As we proceed to tackle this wicked problem of mitigating the atmospheric carbon buildup and reducing it, there's an opportunity to reward all the hands contributing to its wicked solution. At this point, I want to shout out to the folks who've made the growth of biochars as a climate mitigation solution successful. The U.S. Forest Service, USDA, and departments of energy in the U.S. have made major contributions from a funding standpoint to moving biochar from an idea and hobby interest to an industry and a widely accepted product with a host of applications and uses. Their support has been invaluable in positioning the industry and the product as valuable solutions to a host of issues. US and IBI have been the on-the-ground advocates for the understanding of biochars as a product and as a CDR technology, as have the other national organizations, rather under IBI's umbrella. Lastly, thanks for watching this presentation. If you have any questions or feedback, let me know. I'd also encourage you to sign up for our monthly newsletter, highlighting not only biochar, but a host of science-based reports and perspectives on natural resources and land use. Thanks again.